Let's start by determining chiral centers in the following structure. The first thing we want to do is define the term chiral carbon. A chiral carbon is a carbon bound to 4 different groups. The next step is we want to go ahead and draw the hydrogens. Now we can do a process of elimination. So since it needs 4 different groups, we're going to rule out any double bonds. This carbon has a double bond, so does this, so does this, and this. So do these two. And now we're going to go ahead and rule out any of them that have 2 H's. 2 hydrogens, because those are obviously not different, so there we go. Everything remaining should be a chiral carbon that is bound to 4 different groups. This is bound to OH, H, and then remember that when it's bound to this, it's bound to everything from this side, and it's bound to everything from that side. So in essence, this is a chiral carbon, 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 and this is a chiral carbon. The next problem we're going to work on says to translate the given conformer to its eclipsed Newman projection. So they've already started the Newman projection. And the thing about Newman projections is when you have a wedge, this is going to be placed on the right side. When you have a dash, this is placed on the left side. And when you have a line, this is placed on the top. Or the bottom. Anyway, since a Newman projection, you're going to use the perspective that they're giving you. So an eye can be placed here, asking you to look at it from this perspective, or it can be placed here, asking you to look down at it from this perspective. Either way, these carbons are parallel to each other, so this carbon and the other carbon, you're not going to see them. Instead, you're just going to look at these, basically. In this case, we see that the things drawn behind the circle are HH and CH3. This corresponds to this part of the molecule. In this case, we see that the H with the line is placed on top, the CH3 is placed on the right side with the wedge, and the other H with the dash is placed on the left side. So in this case, we're looking at it from this perspective. So when we look over here, we see that here the BR has a wedge, and we're going to place it on the right side. The CL has a dash, we're going to place it on the left side. And the H3C is placed on top. So we're gonna put CH3 on the top. Next, we're gonna work on nomenclature. So the thing to remember here is that the long chain is the parent. And we want to put things in alphabetical order. So let's start with this. Here we have 1, 2, 3, 4, 5 carbons, and let's just make here at 2, we're gonna have something. So the way we're going to name this is we're going to call this hexane. No, sorry, pentane. Give me a second. We're going to call this pentane, yes. And since at 2 it has something, it has a line at 2, so this is 2-methyl pentane. Anytime we have a line coming out of the parent, we're going to use a prefix and we're going to add -il. So, like methyl. As a refresher, we're going to go over what the prefixes mean. So meth is 1, eth is 2, prop is 3, but is 4, pent is 5, hex is 6, oct is 8, non is 9, sorry, dec, hept is 7, and dec is 10. Okay. Okay, for your convenience, I've drawn butane, and we're going to go over a few like extra characters. So here we're going to add this thing called the isopropyl. An isopropyl is a propyl that has a different shape to it. So as you know, propyl is 3. So if we wanted a 2-propyl butane, we would do 1, 2, and we would just do 1, 2, 3. This is 2-propyl butane. Now, if we wanted isopropyl, we would do this instead. So now you also have 1, 2, 3 carbons, but they're arranged differently. So now this is a 2-isopropyl butane. This is a 2-butyl butane. Now butane can also take different forms. One of them can be this way. Sorry. So now you have 1, 2, 3, 4, but instead of attaching at the first carbon, it's now attaching at the second carbon. This is called a sec-butyl. So this is now a 2-sec-butyl butane. You can also have an isobutyl. 1, 2, 3, 4. In this case, it's also branched. You can also have a tert butyl. This is branched in 3. I would recommend that you put this list into your note card. Here are some more prefixes and names. This is a cyclohexane, 6 sides. Cyclo is just meaning that it's in a ring structure. Here's a cyclopentane. As a challenge, let's name this molecule. So we'll start off by defining how many carbons are in the parent chain. In this case, 5. So we know that we're going to have a pent. Now we have a double bond here. And with double bonds, you're actually going to want to name them from the lesser side. So in this case, it's going to be 1, 2, 3, but from here it's going to be 1, 2. So we're going to renumber. In this case, this is a 2-pentene. Remember that a carbon bond to a carbon is a alkane, and a carbon double bond to a carbon is an alkene. In this case, because this has a double bond, it's going to go from being a pentane to a 2-pentene. Let's try to name this molecule. Because we know that it has a double bond, we're going to try to number it from the place where we're going to get the least number. Here, if we're going to start at 1, our less number for the double bond is going to be 2. If we start here, this is 1, 2, 3, or 3 until we hit anything. So we're going to number it from this side. 1, 2, 3, 4, 5, 6, 7, 8. So we know we have a octene on our hand. In this case, there exists a double bond at 2 and 5. And there exists a methyl at 3 and 6. In this case, the M comes before O, L, M, and OP. So we're going to go ahead and name this. We're going to name this 3 6 methyl 2 5 octa. Because we have 2, we're going to actually put the prefix di here. Diene. Three, 6. This will also be di. Dimethyl. Let's start with the problems we're giving. So here is cis 1,3 diethyl cyclopentane. pentane, yes, okay. Let's draw a pentane. If it will let me. So we have a pentane. Let's number 1, 2, 3, 4, 5. Here's saying we have a diethyl. Di just means there's 2 of us. Ethyl means it has 2 branches coming from it. So here at 1, 1, 2, and at 3, 1, 2. Now the cis here means that they're going to open in the same way. This is opening up, so this is also going to be opening up. In this case, to show that these are both in the front, we're going to actually draw a dash, because dashes mean that something is coming towards us. If this were trans, we could easily just replace this with a dash and a line. This line, this dash also represents a line. It is just depicting whether it is cis or trans. Okay, let's work on the next example. So we know this is a nonane. So we're going to draw 9, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 6, 7, 8, 9. Now we know here that it says that at 2 there's a methyl group. So we're just going to go ahead and put a methyl at 2. We know at 5 there's an isopropyl. So at 5 we're going to draw an isopropyl. Okay, let's work on our next one. 6 bromo, 4 ethyl, 3 methyl octane. So octane, 2, 3, 4, 5, 6, 7, 8. We know at 3 there's a methyl. Put that methyl right there. We know at 6 there's bromo, so Br. We know at 4 there's an ethyl, so 1, 2. Next, we're going to look at chair. And we're going to determine whether it is cis or trans. Remember, chairs have axial and equilateral. Axial and I forget how to spell it. Give me a second. Equatorial. Axials open up and down. And wherever you start, like open up, oh my goodness, open down, open up, open down, open up, open down. Now every molecule is going to have an axial and an equatorial. So, and they're always going to be opposite. So if this opens up, this equatorial, these open, they open at a diagonal. So this is up for them and this is down for them. So if this is going up, this will be going down. If this is going down, this will be going up. This is going up, this is going down, etc. I think the point is taken. For something to be cis, it's going to open in the same direction, and for something to be trans, they're going to be opposites. So here, this is going down, and this is also going down. This is going to be cis. Here, this is going down, this is going up. This will be trans. Going down, cis, and going up, cis. For the next part, we're going to determine whether things are easy or neither. So for the first step, you're going to find the alkene, the double bond of carbon. You're going to identify the priority groups based on atomic number. So the highest number is the priority. And then you're going to determine if they are on the same side or not. If they're on the same side, it's Z. If they're different, it's E. I like to think of it, E stands for enemy. Enemies are on the different sides. Okay, here are the examples. In this case, this is the alkene. So this is going to be one of our priority groups, and this is going to be one of our priority groups. In this case, this one opens down. However, when we look at this, we can't determine if it's opening down or not, because this is a hexane or cyclohexane. So this is neither. In this case, we're going to determine that F and Br are our priority groups. Therefore, this would be E. Here, this is the alkene, alkene, and our priority group here is going to be the OH. On this side, the priority group is also going to be our OH because it has a higher atomic number or atomic mass than just O by itself. In this case, these are both opening down, as you can see, and this is going to make them Z. Alright, the next thing we're going to talk about is the highest energy conformation. So when you're looking at Newman's projections, there's really two things you want to do to determine the energy. So step one is determining whether it's staggered or eclipsed. So if it's staggered, that means that they are directly on top of each other, and if it's eclipsed, then they are not. So this is a eclipsed. I got that backward. So eclipsed, they're going to be right on top of each other. Staggered, they are going to be far from each other. In terms of energy, eclipsed is going to have higher energy. Step two, determine bulky groups. And the more bulky the group is and the closer they are together, the more energy it's going to take, because bulky groups are always, they have a lot of electrons, and electrons are always trying to get away from each other. So if they're eclipsed, that means that the electrons are already pretty close to each other, versus here they have room to spread out. And if the bulky groups are near each other, that just means that you have one big you have one big molecule that is right next to another molecule, and that's going to obviously drive up the energy. Okay, next thing we're going to look at is alkene stability. So alkene stability increases as number of substituents increases. Substituents is referring to the carbon that is going to touch the alkene on either side. In this case, this carbon here, is going to touch this and this, which means it has two substituents. This would make it disubstituted. In this case, this carbon only has one, makes it mono. Substituted. In this case, it has two. in this case, it has 1, 2, and 3, which makes this tri. Substituted. Okay. All right, now we're going to solve a problem that deals with carbocation rearrangement. So here, well, there's 2 things to know. So every carbon is bound to 4 elements. However, this carbon has a plus. When carbon has a plus, that means it only has 3 bonds. So you only have 1 hydrogen here. Now, if you're going to do carbon rearrangement to make this more stable, you want to realize that you can move charges. You can move this charge here, and you can move this charge here. And likewise, you can move one of these what are they called? Alcohol? Yeah. You can move one of these CH3s here, and you can move it here. Okay. Well, would you want to move one of these here? Not really, because this already has. Sometimes you do want to go ahead and draw the hydrogens out. It helps. So you really can't move anything here. Now, can you put this charge here? Well, you can, but it would require that you put the charge here and you will take a hydrogen here. It's kind of inefficient because now you just have a charge there. So what you're going to want to do is you're going to want to take one of these CH3s from this guy, and you're going to put it here. When you do that, now you have 1, 2, 3, 4. This carbon has 4 bonds, thereby it no longer has a plus 1 charge. However, as you can see here, this carbon here only has 3 bonds. Therefore, the charge is transferred here. Okay, now we're going to look at reaction coordinate diagrams. This is going to be free energy. This is going to be the reaction process. Transition states are B and D. The next question is, which step is the rate determining step? So when you're trying to figure the rate determining step, you want to draw a straight line from the apex of your curve down to wherever its base is. Same here. Now what you want to do is the one with the highest is going to be the rate determining step. So in this case it is B. Or sorry, in this case it's step 1, because this is step 1, this is step 2. In this reaction, delta G is greater than 0. The reason is we're going from a smaller number to a bigger number, therefore it's also endothermic. It's going to absorb more energy to become a product than it is a reactant. The KEQ, which represents the products over reactants in this case is going to be less than 1. The reason being is molecules prefer to be in their lower energy states. Therefore, the lower energy states being the reactants in this case, rather than the products, means that there will be less products than reactants, making this a fraction which is going to be less than 1. Here is a simplified analysis. Next, we're going to do substitutions. So when you do substitutions, you want to first define the nucleophile, the electrophile, and the leaving group. Leaving groups, they tend to be halogens or water. Water is sometimes a leaving group. In this case, Cl is the leaving group. Cn tends to have a negative charge and Na has a positive. Because of its negative charge, Cn would be the nucleophile. Na would be the electrophile. Step 2 is to determine the structure of this carbon which the leaving group is attached to. We want to do this, 1, to determine what kind of reaction is going to take place, and 2, sometimes since it can travel between neighbors, we're going to modify where the nucleophile is going to end up. In this case, this carbon is bound to this carbon and this carbon, making it a secondary carbon. Step 3 is to remove the substrate. The substrate is also referred to as the leaving group. In this case, it is Cl. Cl is actually going to take 2 of these electrons and it's going to get out of there. So it no longer has this configuration. It is now going to be Cl minus, and actually it's pretty happy in this position because it has an octet. Cl has 7. It originally has 7 not 7 electrons, but 7. What are they called? The outside, the valence, 7 valence. So Cl minus, it has a great life. Cl minus is it has an octet and it's negative. When you do this, this is going to become positive here. In step 4, we attach the nucleophile. In this case, that is Cn. Cn is negatively charged, making it a nucleophile. Na is an electrophile. In this case, because this is a very strong, it's very strong because this usually in a solution is going to dissociate to Cn plus, Na plus and Cn minus. Because this is very strong, the only thing you will have to do, since it's going to dissociate, is you're going to put the Cn here. Now remember that the Cl had a wedge shape to it, meaning that it was attached to the front position. Now, because the Cl, when it broke off, it stayed here with its negative charge. Another thing with a negative charge would prefer to stay away from it. Therefore, it would much rather attack from the back. And so when we're going to draw the Cn, we would like to give it the opposite. We will give it a dash. In reality, some of it will be dash and some of it will be wedge. Maybe 30-40% dash, 70% wedge. For simplicity, this is the correct answer. In our next example, we're going to follow similar steps. So we're going to identify the leaving group slash the substrate. This is the substrate. Remember, it's usually a halogen or H2O. More than likely, it's going to be Br, Cl, something like that. The Na here, positive, electrophil. This whole thing here, attached to the plus, is going to be the nucleophile. After that, we're going to remove Br. Br is like, hey, give me my electrons. I want to go. And then what we're going to do, we're just going to disassociate this and Na plus OCH3 minus, and we're going to attach the nucleophile. In this case, the nucleophile is OCH3. It's going to lose the minus because it's sharing an electron here. And now what you can do in this other step is just transform this to a bond. Same thing, this is CH3. Your work is finished. Alright, let's do the same thing here. Br leaving group slash, what is the name? Substrate. This is substrate. In this case, this O is going to be our nucleophile. This is going to be, actually, in this case, you don't have any immediate plus. This thing, in this case, this molecule is not going to dissociate. This O is going to remain fixed on this. So since this is the substrate, Br is going to take its 2 electrons and become Br minus, and you're left with this. And then you're going to want to attach the nucleophile. So how you're going to attach the nucleophile is, here, this will have a positive. So you're going to just, positive, you're going to put this O here, O minus, is still in the same configuration it was. And it'll, and we're not going to want to leave this as a line. We want to show that it's coming from O and going to a carbon and going to another carbon. And that will be your final answer. All right, in an elimination, a hydrogen is taken by a base and it forms a double bond. In this case, this is the base. Now, it doesn't directly steal from this carbon. In most cases, we will get to the ones where it does. The way you can determine that is okay, here is a kind of good difference I found if you want to know if where will the double bond be. I recommend some videos and things. In this case, this is a strong base. It's going to want to take one of these H's from a neighboring carbon to this Br group. So it steals a bit an H. And when it steals an H, there's going to be a double bond formed here. Now this carbon can't have 5 bonds, so it's going to let go of this Br. And the Br minus is going to be here. Yeah, that's all. Okay. By the way, this hydrogen, when it leaves, we know that usually when we depict something leaving, we depict it as taking the electrons. In the elimination, the hydrogen actually gives its electrons. That is why here you're not seeing anything wrong. There's 1, 2, 3, 4 bonds, but only 3 things connecting. This is actually connecting to these 2 lone pairs that are left behind, called beta. This is called the beta electrons, and they're connecting here to the alpha electrons. Okay. In the next example, this molecule is more bulky, and it's not going to really want to get here. It's kind of going to resist stealing from neighbors. This one is going to directly steal. It's going to directly steal Br. And in this case, this Br is going to give its 2 electrons and become negative, and then join here with this O. And when it does that, you're just going to have a bond to 2 electrons, and you can just depict it as 2 lines. 2 lines. In this case, Br is here, and so this OCH3 is going to steal this hydrogen from this carbon here. The hydrogen is going to give its 2 electrons and join here, thereby giving a double bond. And when it gives this double bond, remember there's a hydrogen here as well. This Br is going to remove itself. and become Br minus. I know it wasn't a great explanation. I recommend watching different videos because there are SN1, SN2, E1, and E2 reactions. Let's move on. Okay, in the next example, we are asked to draw a mechanism. In this case, Br gives its electrons and becomes Br minus. This is going to form plus. Actually, we're going to want to show all of this work, so Br. Following that. Actually, we're going to do a carbon relocation. So here, alright, I drew it wrong. So when this Br gives away, the whole thing is wrong actually. Let's start over. Br takes electrons. I'm still on elimination, my bad. And when Br takes electrons, it's going to be Br minus. There's no bond here. This is able to take bonds from its neighbors. In this case, this is its neighbor, this is its neighbor. It's actually going to do a carbon relocation, and it's going to steal this bond right here from its neighbor. And now it's positive. Here. Because remember, 1, 2, 3, 4. And once you take away this bond, this will become positive. Now we're going to get this CH3OH is going to attack Once it does that, this H is actually going to give its electrons here to O, and this Br minus is going to take the H. Resulting in that. Okay. All right, we're going to take a look at identical molecules, constitutional isomers, enantiomers, and diastereomers. Okay, identical. if you want to know if something is identical, let's say you have a carbon, H. This has F, Br, and H. And here Alright, on first look, you're going to think, oh, this is a chiral carbon, and they've completely switched positions. Here's what a model is in use. So this is the model. This is the CH3. This here, red can be the bromine, and green can be the fluorine. Now, in this situation, the fluorine is facing towards us. The hydrogen is neutral, and the bromine is away from us. So fluorine is, well, for you, this is how it will look. Fluorine is towards you, bromine is away from you, and hydrogen is straight up. So we'll put that there. And now in this molecule, it's flipped. Actually, this goes this way. And then yeah, this is how it will look for you now. Okay. In this molecule, it's reverse. So we have CH3, we have the bromine facing towards us, we have the fluorine facing away from us, and we have the hydrogen facing straight down. And despite the position differences, you can see that these are the same, and we can overlap them. And anytime you can overlap a molecule, and it's the same molecule. So either with a model or by somehow rotating through your mind, figure out, first identify, is this thing identical? Constitutional isomers are, well, you're very familiar with that. They have constitutional isomers have the same chemical formula and a different attachment. This is an example of a constitutional isomer. 1, 2, 3, 4, 5, 6, 7. 7 carbons, and 1, 2, 3, 4, 5, 6, 7. 7 carbons and 16 hydrogens on both, but they're arranged very differently. Now we will talk about stereoisomers. Very simple. So you're going to use a flow chart. You're going to ask yourself, is this molecule a mirror image? We will get to what that means later. Yes, then you have an enantiomer. No, you have a diastereomer. There's 2 ways to know that you have an enantiomer. So the first one is if you have something like carbon, Br, you have H, H3C, and you have a veg. This veg is OH. Here you have HO, H, CH3, BR. Okay, now if you can notice, BR and CH3 remain the same, while H and O switched places. Oh. Yeah. They came to this, in this side of it, so if you were to flip this atom around, you could not displace it onto this anymore. It would become these are mirror images, but they aren't, they're not the same. What you can do is, let me pull up a good example. So if you can get something in a line structure and you can you can switch every single thing that it has into its opposite, then you have an enantiomer. Say you had something else here that was like a wedge O, and if it were a dash O, you have an enantiomer. Now if this was not, if this was kept the same and everything else was mirrored, you don't have an enantiomer, you have a whatever it's called, I'm finding it. Diastereomer. Okay, you know what I mean. So in this first example, you can identify the parent chain. So it's going to go 1, 2, 3, 4, 5, 6. And here it can do the same. 1, 2, 3, 4, 5, 6. So while this looks like it could be a constitutional isomer, actually the parent chain has now, the longest chain now has 1, 2, 3, 4, 5, 6 carbons. Making this a diastereomer. It's a diastereomer because it's not mirrored, but it's still the same compound, basically. These are going to be the same because you have something that is looking forward. Now, if this was on this side, you would have an enantiomer. But if you notice, if you have something that's rectangular and you have something that's coming towards you, and you flip it, you're going to now have it facing away from you. So once you flip this back around, you flip it back around, what was now facing away is going to face forward. These are identical. In this case, you can identify if this is an enantiomer or not. So we know that this is a stereoisomer, but is it a mirror? So we notice that OH is the same. This CH3 is changing, is opposite. And this one, it is opposite. But since we do have this OH that is not changing, we're going to call this a diastereomer instead. Next, we're going to label the alkyl halide. This is going to be this carbon right here attached to this halogen. Okay, so it's attached to 1 carbon, 2 carbon, 3 carbon. It's going to be it's going to be tertiary, so you can just write this. Now we're going to focus on this, and okay, so in this case, we know that there's a H. We're not going to worry about it. We just want to define which one is 1, 2, and 3. In this case, we want to define which one of these. We know that the Cl is 1. We want to know which one is 2 and which one is 3. So we're going to go down. We're going to see these are both attached to carbon. Okay, go down again. And these are both again attached to carbon. Okay, and then we want to go down again. We realize this one is attached to carbon, and we realize this one is attached to bromine. Therefore, this one would be heavier. So we're going to assign this as 2, and we're going to assign this as 3. Now, coming from chlorine, we are going to move this way. And from chlorine's perspective, that would be to the left. Therefore, this is going to be S. Here, we're not going to worry about this H, but we are going to worry about these 3. So we know that this one is going to be 3 because O is much larger than C by about 4. We know that since this O has a double bond, it will weigh less because this OH has a single bond requiring this carbon to have 2 more hydrogens attached to it, versus this carbon only has 1 more hydrogen. So this is going to be 1, 2, and 3. And if we're starting here at 1, we are again moving to the left. If we were moving to the right, we'd go this way. So we are moving to the left, we're connecting 1, 2, 3, going this way, counterclockwise, making both of these S.